Welcome back to video lesson number 2. We're going to start talking about acid-base strength. Now you may remember from your conversations in previous chemistry courses that the strength of an acid and base is not based on the concentration of the acid or base, but instead it's based on how much ionizes when the acid is put into water. Which means if an acid ionizes or is very, very soluble, it is considered to be a strong acid or strong base. But if an acid has a very, very low percent ionization, meaning it tends to stay together rather than split into its individual ions, then it's considered to be a weak acid. Here are some examples of strong and weak acids. Your example of strong acids include HCl, HNO3, and HClO3. Weak acids are HF, H2CO3, and this one, which is a common weak acid known as acetic acid. Sometimes acetic acid is written as HC2H3O2, but also sometimes written as you see it here, CH3COOH. Here's an example of a weak acid, and usually you would include water as a reactant here, and the water then creates H3O plus and F minus on the product side, but we've removed the water just to simplify the reaction a little bit. Now this acid is considered a weak acid, which means that acids, when dissolved, form a dynamic equilibrium between the reactant, the acid molecule, and the product, the ionic form. And so this dynamic equilibrium sets up, and the equilibrium can be expressed as an equilibrium constant, but we have specific equilibrium constants for acids and bases. We call them Kas or Kbs for bases. Now typically weak acids have Kas that are much, much smaller than 1, where strong acids have Kas that are much, much larger than 1. For example, HCl ionizes, and this doesn't reach a dynamic equilibrium because it ionizes completely. And so all of the HCl that hits water splits up into H plus and Cl minus. And so we say that's a strong acid, or its Ka, its equilibrium constant, is much, much larger than 1. And remember, when you have a very, very large equilibrium constant, that basically means that you have lots and lots of products and not much for reactants. And so that makes sense, that if the expression is products over reactants, then you have lots of products and barely any reactants. I'd also like to point out at this time that there are things that contain hydrogen but are not considered acids at all, and those are what we call the non-acids. And because they don't dissolve, they are not considered to be acidic, because you have to produce H plus in order to be acidic. Some examples of the non-acids are like CH4 and even just hydrogen gas. These two compounds are considered to be non-acids. Let's dive deeper a little bit more into the concept of Ka and Kb. Remember, these are equilibrium constants specifically for acids and bases. Once again, the general form for an acid dissociation looks like this. You've got the aqueous form of the acid, where the ions are together, and the ionic form, where the acid has split up into plus and minus ions. And this is in dynamic equilibrium. And so you can have a Ka expression which expresses the concentration of the H plus times the concentration of the A minus over the concentration of the original acid. The same sort of relationship exists for bases. If you have a general base, a BOH split up in dynamic equilibrium, you've got B plus and OH minus over the original concentration of the base. The equilibrium expression for a base is Kb is equal to this. Once again, products over reactants. And we mentioned this on the last slide, but it's worth repeating, that if the Ka is really, really big, then it's considered to be a strong acid, and if the Ka/Kb is really, really small, we consider that to be a weak acid. Take a moment now to talk about the relationship between the Ka and Kb, and specifically the Ka and Kb of conjugates. For example, the weak acid, hydrofluoric acid, when dropped into water makes H3O plus and F minus. We've been writing this just as HF gives you H plus and F minus, taking out the water as a reactant and taking out the water from the hydronium just to clear things up and clean things up. Water is not included oftentimes because we just assume that it's there as a reactant and we assume it's attached to the H plus. But if you're looking at the conjugate acid, the acid and the conjugate base, the acid is the HF and its conjugate base is the F minus. Now, as we talked about on the last slide, because it's a weak acid, it has a Ka value. And the Ka value is less than 1. But it does have a Ka value. That Ka value is actually 6.6 times 10 to the negative fourth. Now, because HF, the acid being the proton donor, is an acid and has a Ka, its conjugate base pair, also has a K value. It has a Kb value. Essentially, if the reaction proceeded back to the left, because this is a weak acid, so it should be in dynamic equilibrium, that if it proceeded back to the left, it would represent its equilibrium constant as a base. The number for Kb for F minus is 1.5 times 10 to the negative 11th. Now, what's interesting about the Ka-Kb relationship of conjugates is that if you take the Ka and multiply it by the Kb of an acid-base conjugate pair, what you get is always 1 times 10 to the negative 14th, which is referred to as Kw, also the autoionization constant for water. Now, the Kw constant gets its name, autoionization constant for water, from the reaction of which water autoionizes itself. Consider two molecules of water reacting with one another. If the first water is an acid, then we label it A, which means it's a proton donor, and it will donate its proton to the other water. That makes this the conjugate base. And because water number 2 received the proton, that makes it a base, and it can be paired with its conjugate acid. Now, what's interesting is that the concentration of H3O plus and OH minus in a solution where water is autoionizing itself is 1 times 10 to the negative 7th molar. And that is true for both, because you'd expect if one is 1 times 10 to the negative 7th, then the other is 1 times 10 to the negative 7th. Now, if you set up the equilibrium expression for water, what you have is the concentration of H3O plus times the concentration of OH minus over 1, since these are both liquids. They're not part of the equilibrium expression. And if you take 1 times 10 to the negative 7th times 1 times 10 to the negative 7th, you get 1 times 10 to the negative 14th, which is also defined as Kw. Now, you might be asking yourself, what's the connection between Kw? Because this makes sense for water. It makes sense for water because you have concentrations of the conjugate acid and conjugate base. These are aqueous solutions of each, and you can assign an equilibrium expression and an equilibrium constant to aqueous solutions. But what's the connection between this 10 to the negative 14th and this 10 to the negative 14th? And in order to explain that, I need to take a look at water as just H plus and OH minus. This is no different than if you take HA, which is split up into H plus and A minus. But we're going to get rid of that because we want to look at just pure water. Now, to that pure water, I'm going to add some HF to the water. And that hydrofluoric acid is a solution of H plus ions and F minus ions. So I'm going to take that solution and pour it into pure water. Now, pure water is at dynamic equilibrium, so it's reached this state where H plus and OH minus are creating H2O, and H2O is creating H plus and OH minus. But what happens when you add HF to the pure water is you introduce water to an excess of H plus. So the concentration of this goes up. It goes up a little bit. And to relieve the pressure, thinking Le Chatelier's principle, the reaction is going to be stressed and move back to the left. This is going to go down because it's going to try and maintain the Kw constant, the constant being 1 times 10 to the negative 14th. So again, your H plus concentration goes up by the addition of HF to the water. So the H plus goes up. You also add some F minus in there, but that doesn't really affect the acidity or basicity of the solution. You're just adding H plus to the already present H plus in the water autoionizing situation. So you add H to the water, the concentration of H goes up. As a result, the reaction shifts to the left, reducing the OH minus. H plus and OH minus still multiplied together need to equal 10 to the negative 14th because a constant is a constant. Again, this is a Le Chatelier's principle concept. You add some of the product, forces a reaction to the left, the concentration of the OH reduces to keep this number constant. And that's how the connection between HF and water presents itself is because we need to always maintain that concentration constant, equilibrium constant. 1 times 10 to the negative 14th is always a number. So if you increase H, OH has to go down in order to keep this number constant. And so in the conjugate situation, when you add an acid to water, you are simply increasing its H plus concentration, decreasing its OH minus concentration. So for conjugates, the Ka times the Kb has to be the same as the autoionization constant for water, which was down here. So in summary, the relationship that I need you to know how to work is that the Ka times Kb always multiplies to be 1 times 10 to the negative 14th for conjugate acid-base pairs. And if you have a really, really strong acid, your Ka is high. As a result, the Kb of its conjugate is very, very low, and vice versa. If you have a weak acid, which has a low Ka, relatively speaking, it has a relatively high Kb value, because these two always have to be in inverse to one another. As Ka gets higher, Kb gets lower. As Ka gets lower, Kb gets higher. Close look at this little picture coming right from the book. Some things I wanted to point out to you is that we've got a list of acids from the highest, strongest acidity to the lowest acidity on the left. And if you notice right across from it is that you've got its conjugate base listed from lowest to highest. It's that relationship that I just showed you on the last page. So your strong acids listed up here are things where the Ka is very, very high, much, much higher than 1. And those substances, in fact, we never really even talk about their Ka values. They're so high that we just say it's a strong acid. The only time you ever really talk about the Ka of an acid is when it's a weak acid. And the weak acids begin at H3O plus here. These are the ones where the Ka is much, much lower than 1. And it gets smaller and smaller and smaller as you go down until eventually you reach negligible acidity, where it's things that have hydrogen in them but essentially don't dissolve. They have no acidity whatsoever. And things with no acidity, their conjugates are very strong bases. So as acidity decreases, strength of base, or basicity, or even something referred to as alkalinity, which is another word for basicity, increases. And the conjugate pairs are in this delicate dance. As one goes down, the other goes up. As one goes up, the other goes down. Now we've got to the point where it's time to start calculating pH. And you'll remember a lot of these formulas from last year's chemistry course, or a chemistry course that you took previously. pH, by definition, is the measure of how much H plus or OH minus is in a solution. It is a way to turn something that's a very, very difficult molarity to understand into a number that normal everyday people can understand. So you may be familiar with the pH scale. The pH scale runs from 0 up to 14, where 7 is right in the middle. Anything considered to have a pH below 7 is acidic, and anything that's above 7 is basic. You might also refer to basic as alkaline. They mean the same thing. You may remember that in order to calculate the pH of a solution, all you need to do is take the negative log in base 10 of the concentration of that H plus solution. That's assuming you know the concentration of the H plus in solution. For strong acids, this number is the concentration of the acid. But this number is not the same for the concentration of a weak acid, which we'll talk about here in an upcoming video slide. Now, for pOH, which is something that you use to express the concentration of OH in a solution, it's the same thing. It's log, base 10 log of OH concentration. Now, the inverse relationships of these are also true. If you know the pH and you want to calculate the H plus concentration, you just take 10 to the negative pH power to find the H plus. And the same goes for pOH. If you know the pOH and you're trying to calculate the OH minus concentration, you simply take 10 to the negative pOH power. And as you might have deduced from our conversation about the Ka and Kb values of acids and conjugate bases, the pH of an acid is equal to 14 minus the pOH of its conjugate base. So in other words, if you take the pH of an acid and add it to the pOH of its conjugate base, it should and always will equal 14. Now with that being said, let's take a look at a couple of just basic practice problems. Let's say you have the concentration of H plus in solution as like 0.000501 molar. What's the pH? Well, you take the negative log of 0.000501 and you get the pH, which is equal to 2.300. Now, if I asked you what's the pOH of this very same solution, well, I just simply take 14 minus the pH to find the pOH, which is 11.700. And that number represents the concentration of the conjugate base in the solution. On the other hand, if I tell you the pH of a solution is like 7.35 and I ask you what's the H plus concentration, well, you just take 10 to the negative 7.35 power and you'll get 4.7 times 10 to the negative 8th molar. Now let's have a conversation about significant figures. Now, when it comes to logs, significant figures are kind of thrown out the window. Not necessarily thrown out the window, but they're really, really weird. And they're pretty nitpicky about this. In fact, they're so nitpicky about this on the AP exam that they don't give you the plus or minus 1 sig fig when you're going from log to pH or from molarity to pH. So take a close look. This is 3 significant figures, 501. The first zeros are not significant, so there are 3 sig figs. I'll underline them here. Now, when it comes to reporting a pH to the proper number of significant figures, it's based on the numbers after the decimal. So when you translate from 3 significant figures to a pH with 3 significant figures, it represents the numbers to the right of the decimal. So if you need 3 sig figs, you go 3 past the decimal. Same is true with this situation down here on the bottom. I had a pH. How many sig figs are in here? Only 2, because I only have 2 digits to the right of the decimal. So when I report my answer in the form of molarity, I can only report it to 2 sig figs, or 4.7. Excuse me, it should be 4.47 or 4.5. So let me just fix that quick. 4.5 times 10 to the negative 8th. So in summary, for sig figs, they only count starting at the decimal. And if you want 3 sig figs, you got to go 3 digits past the decimal of a pH or pOH.